Okay, so the live stream should have begun right now. And I'll also try to take a recording of the Google meeting, so it should record the presentation as well. And we'll see which one has a better quality. All right. Okay. All right, everyone. Thank you for joining us virtually. I realize this is a big adjustment, and I thank you so much for cooperating to kind of use this Google Meet forum to join. It really makes our life a lot easier. um, I realize it's the first time we're doing this, so it's going to be a little bit of adjustment for all of us, certainly for me. So please bear with me. I had a very ambitious set of slides for this week, but I'm not sure I'm going to get through all of them because I want to make sure that since it's the first time we're trying this, that everything goes smoothly and everyone is understanding everything clearly. All right. Um, hold on. Okay. And with that, let's begin. So this is week 13, and we have taken a look at regression so far, and we've played around with it a little bit. We've played around with the residuals coming out of regression, and I think in your homework assignment for today, you got a glimpse of those residuals and what they look like, and potentially how to interpret them. Okay, so I'd like to talk about that a little bit further, and then we'll kind of enter some other topics. Once again, I'm not going to try to muscle my way through all the material I have today because I really don't know um, how different this will be and how if people's comprehension is different. A couple of things before we begin. If you have a question, please click the raise hand button. There's a little button called raise hand. I'll raise my hand right now, and you can play with that right now if you like. Um, and I can also lower you. I can lower your hands. I cannot raise your hands. Okay. So if you have questions, please raise your hands. And my TAs, if I may ask you, if I'm ignoring hands that are raised, please find a natural break to interrupt me. Um, Maybe not in the middle of a sentence, but find a natural break to interrupt me. If your hand is raised for some time and no one is noticing it, whoever you are, you're welcome to unmute yourself and say, "Excuse me, I've got a question," so that I get your attention. Okay. What else is there other than raised hands? Please keep yourself muted, but keep your camera on so that I can see you. All right. Anything else? I mentioned earlier that there's a turn on captions button. Right next to raise hand, there's a button on Google Meet to turn on. It's got CC in it. And if you press that button, you will see my words written on the screen as I'm speaking to you, if that makes your life easier. All right. Um, and the last thing, which I think I mentioned on the announcement that I sent out, is that if you have roommates or anybody who might be embarrassed to be suddenly caught on camera, please turn on virtual backgrounds. Okay. But otherwise, please do turn your cameras on. All right. So could I ask everyone just to turn on their camera or to make sure that your camera is turned on? Okay. All right. Okay. Could I ask a few more people to turn their cameras on? All right, good. Um, Before I get started, any questions about using Google Meet? Does anybody have any questions? You're welcome to raise your hand. Nobody? You are all confident you know how to use it? Okay, fantastic. So let's get started. This week we're going to be entering into some more topics around regression, but you'll see that these are topics that we'll come back to later in the semester in a few interesting ways. So let's get started. All right. So we've been looking at regression models so far, and I haven't really explained what I mean by model yet. All right. We obviously ran the code for regression. but we didn't actually ever really formally discuss what is this model, what is it trying to do. So what is it trying to do? Let's take a look at it. So if you look at the slide, you'll see that our regression models typically look something like this, all right? And in it, we have obviously a dependent variable, and we have a whole set of independent variables as well. And we have an intercept, and we have a residual term, which we often call an error term as well, right? Um, and one of the things I'd like to kind of ask is, what are these different parts of this model, and what is the purpose of this model? Like, what are we trying to do with this? Okay, so a brief explanation might simply be that we have some kind of dependent variable like the miles per gallon of a car, and we're trying to understand what are the different factors, what are the different variables that explain why miles per gallon in a particular car is high or it's low or it's average. What is the level of miles per gallon and how is it related to other things, okay? Um, there's two ways that these kind of models can be used. So I want to be clear about which way we're going to be using it in this class, all right? One way in which these models can be used is to actually try to explain why miles per gallon is high for some cars, why it's low for some cars. So we might have explanations like, well, there's a car which has, let's say, heavy displacement, it's got a really big engine, so it's going to be less fuel efficient. That could be a possible explanation, and we hope that this model will be able to detect that there's a relationship between displacement and miles per gallon based on the coefficient. All right. So that's one way to think about what this model is trying to do. We've got a whole bunch of variables, independent variables here, and we're trying to understand which of these is related to miles per gallon. All right. Um, there's something not quite satisfactory about this explanation of the model to me. First of all, is this model trying to explain which of these things is related to miles per gallon, or is it trying to explain which of these independent variables is, oh, by the way, I have a little typo here. This should not be independent. This should be independent, one word. Okay, so apologies for that. So is it trying to explain which of these independent variables is just correlated with miles per gallon, or is it trying to explain which of these causes miles per gallon to go up or go down? Let's try to take a little vote. How many of you feel that this model is only trying to explain which of these variables is correlated with miles per gallon, not it causes miles per gallon? Would you like to raise your hand? All right. Yeah, we have a few correlated. Great. Awesome. All right. So we've got several people who feel that model is essentially trying to show how things are correlated. Okay. So, excuse me. All right. So let me next ask, how many of you feel that this is a causal model? This is trying to show which of these factors causes miles per gallon to go up. Any hands? All right, we've got some hands. So how many of you feel this is a model trying to show what causes miles per gallon to go up? All right, we've got more hands. Excellent. Well, we're kind of tied. We have a fairly equivalent number of hands of people who feel that this is a correlational model and this is a causal model. All right. Which one is it? It's complicated. um, first of all, indeed, if we look at if all these variables are truly independent, this model will tell us which of these is correlated with miles per gallon. It'll certainly say that to us, okay? However, we don't really need a regression model if we are only interested in which of these factors is correlated with miles per gallon. What else could we look at? One thing we could look at is we could simply look at the correlation table. And in fact, the correlation table can also tell us if there are significant correlations between the independent variables and the miles per gallon. Okay, so while it's true that the regression model can tell us what is correlated with miles per gallon, it's overkill. We don't really need this just to find out what's correlated. The correlation table already says that to us. What the regression model is trying to do a little bit more of is to say um, which of these, the relation model, the regression model is really leaning more towards trying to explain what is causing miles per gallon to be the way it is. All right, so we think of this more as a causal model. What causes miles per gallon to happen? Okay, so first of all, in terms of the purpose of an explanatory model, so if you're trying to use this model to explain something, then we should think of this as a causal model, not a correlational model alone. All right. Couple more questions. What else could this model be used for? Well, this model, as is written here, doesn't need to be used only for um, explanation. And maybe many of the people who were saying this is a model for correlation, maybe you're thinking of this later, this other explanation, which is that this kind of model can also be used for prediction. We can also say, well, I have a car. I don't know its miles per gallon right now. Maybe because the car hasn't been released yet. Okay, maybe it's a car that Toyota or somebody is going to release in the near future, but it hasn't come out yet. So what I could do is, if I know already how many cylinders it has, what its displacement, horsepower, if I know all these things, maybe I can make a prediction of what miles per gallon should be. All right. So this could be used for prediction purposes too. I'm not going to get much into prediction here, so let's just stick with the causal explanation. All right. So we have a dependent variable that we're trying to explain what causes it, and we have all these independent variables. And again, apologies, this should read independent, not independent. Okay. We have all these independent variables which are trying to um, which we suspect could be causes for miles per gallon to be different between different cars. And in the end, we have these error terms. So what are these error terms? Generally speaking, these error terms we think of this as the regression error, meaning, well, the regression is going to be wrong about each car by a little bit, and this vector of errors will tell you for each car how wrong the regression model is, okay? That's one way of thinking about this residual term or this error term. And the way I just explained it, it really does sound like an error. However, there's one more way to think about it, and I really like this other explanation, and I'll really exploit this second explanation a little bit today. The other way to think about this error term is this term is capturing all the other explanations of miles per gallon that is not represented by these independent variables. So if there are any other explanations for miles per gallon, they will all be grouped together and captured by this error term. All right. So that's hopefully that's another interpretation of what this error term is. And I'll show you a little later today how we can use this in a really powerful way to solve some problems that we sometimes have with regression. Okay. All right. Um, and by the way, if you have a question, you can raise your hand. You can also you can also you can also just write into the chat box. Matthias and I will try to keep an eye on both if there are hands raised and if there are messages in the chat box, okay? Or what you could do is, yeah, so do one or the other. Raise your hand if you'd like to ask a question live, or just write into the chat box if you have a question. The chat box is right next to the People tab, so it's on the top right, it's on the right-hand menu, and there'll be a button called Chat. All right, okay. I have a couple more questions about this kind of a model. So, but before I ask those questions, any questions on what I've asked so far? Anybody? All right. So my next question is, who picked these independent variables? Like, why were these independent variables picked? Could I ask somebody to give me a guess as to why these independent variables were picked for this model. Like, why have I written, let me be more specific. Why have I written down these independent variables in my model? What makes me think that these are suitable independent variables in the model? Does anybody want to take a guess? I'll wait a little bit. Stephanie, please unmute yourself and then give us a guess. Oh, okay, thank you so much. Um, that's a really good answer. And actually, there's two answers that Stephanie put in there, and I want to explore both of them a little bit. Okay. One thing that Stephanie said is that, or maybe I'm interpreting a little bit what Stephanie mentioned. So Stephanie, feel free to interrupt me or raise your hand if you feel I'm mischaracterizing it. But one explanation she gave is that maybe I have some expertise about what miles per gallon could be, so I picked these variables because I believe these are the important variables. So I'm using like my expert thinking about what I know about car engines and how cars work. Okay, so that's one possible reason these variables are in the regression model. However, Stephanie started saying another thing in the middle, and it's another very curious answer, which is these might also just be the variables that I can measure. Like I already have them measured for some reason. So maybe it's just convenient that I happen to have these already measured or known, so I'm using it. All right. So which one is it? Is it that I am potentially an expert on cars and I pick these because I think these are going to be the best explanations? Or is it that these were the easiest ones to measure? I mean, I can literally just go Google and find these ones, and I don't know some other ones. Which is a better explanation? I think in this case, in almost all cases, not almost, in all cases, it's usually a combination of those two. On the one hand, we do want to use our expertise and say some variables are going to be better explanations than other variables. On the other hand, we just cannot measure everything. All right. So we cannot measure everything. So we just also pick the variables that we can measure easily and conveniently. So it's usually some mix of these two reasons why we pick certain set of independent variables. All right. So the two answers then are expertise and convenience. All right. And I'll be quite honest with you, a lot of scientific research, in fact, a lot of researchers in companies or in universities, researchers, the second explanation of convenience is usually the stronger explanation to some degree, because a lot of researchers who want to play with data, they don't have the ability to go and generate data that they actually need. So they're just kind of asking, hey, what data do we already have? Let me just pick from those variables. All right. A simple example might be like in a company, let's say Netflix, right? Let's say Netflix wants to kind of decide what movies to show you. It can, of course, use that kind of collaborative filtering thing that we saw before, which is it can look at what are the movies have you seen on Netflix. It could also add some more variables to that, such as what is your rating, up or thumbs down? What is your rating of different movies? And it could also use some other characteristics like what country are you in, what's your gender, what's your age, etc. How long have you been watching Netflix? How long have you been a customer of Netflix, etc. Okay. However, there's a lot of things that Netflix cannot know about you. It cannot know about your general taste in movies outside of Netflix. It doesn't know what movies you went to the theater to watch. It doesn't know what movies you sat around with your friends and watched on a DVD or something like that. So it doesn't know a lot of other things about you, which could help it have much better explanations or predictions. So for the large part, Netflix is just doing what is convenient. It's just using whatever variables its platform can collect and just using those. All right. So it's a big part of convenience. But then once we have the variables we can conveniently measure, we do ask ourselves which one of these makes most sense has some logical explanation for why it would affect miles per gallon. Okay, so that's this question. Any thoughts about this question, anybody? All right, I have a second question. What about all the stuff we didn't measure? Like, there might be a lot of other factors we haven't measured. Um, are those going to affect our regression? So, for example, what if different people are driving these cars using different types of gasoline? Like, I think for those of you who drive a scooter or a car, you probably know that there are different grades of gasoline. You go to the gas station and you can pick, I forgot what you can pick, like 85, 90, 95. Like, you can pick different grades of gasoline as well. We're not measuring that here. We're not measuring what grade of gasoline people are using, all right? Any other possible variables we are not measuring that could really determine miles per gallon? I'll measure another driver level variable, which is how aggressively you drive. Okay, like, do you like hit the gas really hard and hit the brake really hard, like you're a really aggressive driver, or do you drive very softly and gently and don't speed up too much? You let the car naturally decelerate, and things like that. So how you drive the car also has an impact, but it's not in our model. All right. But let's not think about the driver level. Let's go back to the car level. Any other things that we could be measuring? I'd like to hear one more guess from anybody of what we could be measuring in terms of miles per gallon of a car. In fact, you could even tell me any factor that is not written here that could affect the performance of a car in any way, and we can see if it affects miles per gallon. Anybody? I'll take a little break to wait for an answer. Stephanie, go ahead, please. Oh yeah, okay, I just mentioned that one. So 85, 90, 95, that's the quality of the gasoline. Yes. So that's the words I meant to use. Quality of the gasoline. Yes. Anybody else? Um, when you let's say for example, let's think of performance of the car in general. When you look at a car, you can sometimes tell if a car is a sports car or if it's not a sports car. What are some of the things you can like see at a car, look at it and say, this is a sports car, it's gonna have high performance. What is some of the things that you can kind of visually see in a car? Anybody? Oh, there's some stuff written in the chat. Let me go take a look at the chat. Brand. All right. Okay. Um, The shape of the car, Billy. Yes, thank you. The shape of the car. So the brand of the car is possible. I believe. Oh yeah, and we do have. We could find out the brand from the name of the car. I believe I don't remember the name of the car in our data set actually has the brand in it. However, I believe there aren't too many cars of the same brand in our data set, unfortunately. Nianqing, that was a good guess. The second guess was Billy for the shape of the car. Yes, the shape of the car. If you have two cars and you shape one like a big brick and you shape one like a fighter jet, you're going to get different performance characteristics. And certainly, cars with a sleeker shape will have a more will have better performance and also better miles per gallon as well. But shape of the car isn't in the model. So Billy or anyone else, what will happen to this model if we don't include other important things like shape of the car? Anybody would like to take a guess? What will happen to this model? Will this model be completely wrong? Any thoughts? So just for the sake of time, let me try to answer my own question. One thing is, if uh, if cars all have different shapes, some are blocky, some are sleek, then this residual term should pick it up. That error term will be bigger because there are important factors that the other independent variables are not picking up. All right. So that's kind of where those other factors are going. All right. So, okay, so that's what I'll say about this right now. So these are picked out of convenience and some domain expertise, and all the factors we're missing should hopefully go into our error term. All right, okay. Yes, Genu, it'll become in here, all right. Billy horsepower is actually in our model right here. All right, okay. All right, let's move on. So this is a regression model. I'm going to come back to this question of what is the model, though, trying to do and what is it not trying to do. All right. And I'll come back to this question in a little bit. Let's move on to actually see some things that we tried on our homework. Okay. So one of the things we tried on our homework is that we tried to run a regression on all this data, both in with raw units as we had before. And this time I also asked you to try to log transform the data and see how that produces a different results. All right. And some things that I think you probably noticed that is happening here. One thing is when we well, first of all, with the raw data, we had several issues. I think this circle is a little bit off, but it's kind of telling us that a lot of these relationships are non-linear. So we're not really getting good estimates of what those relationships are. So that's one issue. Um, and of course, we had multi-collinearity problems in here as well. Okay. The second thing is that so then when we log transform this data, so we just take this data and I created a new data frame essentially where I'm just taking the log of everything. I'm not taking the log of the model year or the log of the origin because, well, first of all, origin is a factor, so it kind of doesn't make sense to take the log of it. It's not a continuous variable. The model year also kind of to me doesn't make sense to take the log of it because it's just like year by year, so it's very hard to describe. Remember, the log tells us percentage change. So if we take the log of the model year, I may or may not be able to interpret it because I'm not sure how to interpret percentage change in model year. So I didn't actually take the log of the model year. It's fine if you did. Maybe you are able to interpret it. So it's fine if you did for the homework, but I did not do that here. Okay, let's move on. So then I took ran the regression again, and I left model year and factor origin the way it is, and I took the log of everything else. All right. And if you look now, if I can zoom into some of these, you'll see that these relationships have become much, much more linear now. There's still some problems here, like with acceleration, but the rest have become considerably better behaved, especially in terms of their relationship with miles per gallon. All right, so that's great. You also notice now that several more factors have suddenly become significant. So for horsepower and for acceleration, these are now actually significant relationships. They were not before. Okay, so trying to view them from a linear point of view has helped our regression model detect that these relationships are actually non-zero. So that's the significance, all right? And what else happens? Well, one thing that also happened is our R squared improved a little bit, okay? You'll notice that our R squared improved. And again, what is R squared? We can think of R squared as a multiple correlation. So it's the correlation, or we can think of R, the big letter R, as the multiple correlation between the dependent variable, miles per gallon, and all the independent variables taken together. Okay, so that multiple correlation between one dependent variable and all the independent variables, this multiple correlation is called R, and if you square it, then it's actually a variance explained. So when we square it, R squared actually is also SSR over SST. So it's the amount of our total variance, variability, I should say, of miles per gallon as it is explained by all the other variables. All right. So the amount of miles per gallons or log miles per gallons in this case variance has improved. So our multiple R squared has actually improved in this model by improving the linearity of all the relationships. Okay, so these are some good things to say about taking the log. And the interpretations are also not too difficult. The interpretations are, for example, with weight, it would be um, I believe a 1% change in weight will reduce miles per gallon by 0.5%, something like this. All right, so that's the kind of interpretation of these coefficients now, is that they're by percent. All right, so that's what we're getting from doing a log of this. Any questions on what you're seeing here so far? Anybody? I'll take just a quick break to drink some water and see if there's any questions. All right. Okay. All right. Let's move on. So I also asked you to kind of look at some of these relationships, some bivariate relationships in a little bit more detail. Okay. I asked you if you could do a similar thing, but just this time regressing miles per gallon over weight and only weight alone, and see the difference between it as a nonlinear relationship and a linear relationship. All right. So when we take the raw data, you notice that there's this kind of banana shaped curve to the data. And you also notice that the residuals themselves, if we plot it in these two ways, have some issues. For example, the residuals here are not symmetrically centered around zero, okay? Zero being the horizontal line here. The residuals, which are on the y-axis here, kind of have a shape. So there's a pattern. There's some kind of relationship between the independent variable and the residuals. And this is a no-no for regression. So in regression, if you want to interpret the coefficients correctly, you cannot have a relationship between the residuals and the independent variables. So there's a problem here with this data. And when we do the density plot, we also notice a skew. All right, and it's kind of non-symmetric. And when we take the log of miles per gallon and weight, we notice the residuals improve considerably. The residuals are, to a certain degree, much more evenly distributed across different weights. So there's less of a visible relationship between weight and residuals. All right. And they're kind of distributed on both sides of zero. All right. So we have a little question here. Let me see this. Chinya, you asked about acceleration. I'm not sure what the question was. Was it? Oh, it was about this issue over here, right? It was about acceleration, and it's still having a fairly non-linear kind of relationship potentially, even after log transformation, okay? So a couple of things we could do with acceleration. One is we might simply say that, and let me take a look at the log results. So even though we have a significant coefficient for acceleration, we might simply say that that actually we cannot really interpret this correctly because we can visually see that this relationship is not so linear, despite our log transformation. All right. So this is kind of I think we'd have to recognize that as a shortcoming of our regression. And so even though it's significant, we really cannot interpret this coefficient very well, just looking at the visualization itself. Riley, is that a satisfying response or unsatisfying response? All right. Um, okay. All right. So let me move on. So this is a so this is kind of where we are. So we kind of see nonlinearity with some transformations. We can make this more interpretable for us. Okay. There are, by the way, forms of regression or other types of analysis that can actually fit a curve through nonlinear data. Those become much harder to interpret because it's very difficult to interpret a curve. And I'm not going to go into those this semester. All right. Okay, let's talk about multicollinearity for a little bit. So this is all I want to say about nonlinearity, which is to give you an exercise in actually transforming it, trying it, and very importantly, looking at the residuals and convincing yourself that the residuals actually, you see a significant improvement in the residuals. All right. All right. And again, remember that regression, we really cannot interpret the t-values and the p-values or even the coefficients potentially if our residuals are not somewhat normally distributed and symmetrically distributed across zero all along the independent variable. All right, so here we are. Okay, what else are we going to do? Um, so let's move on to multi-collinearity, right? And with multi-collinearity, we recognize that several relationships have strong correlations between each other. So that was when we took this, and in this case, we're starting with the log transform data that we had from the earlier question, okay? So when we just take the raw regression, um, we notice that there are going to be a lot of issues with multicollinearity. So in the homework assignment, I made a suggestion that let's try to remove some independent variables by looking at their VIFs and removing the variables which have the biggest VIF values, okay? So once again, a reminder of how VIF works is that in VIF, we are essentially looking at the R squared of one independent variable, not dependent, one of the independent variables regressed over the other independent variables, okay? So why we bother regressing it? Well, remember, once you regress it like this and you get an R squared, first of all, remember that without the square, just the R, the big R, is a multiple correlation. So it tells us how correlated is one independent variable against all the other independent variables, all right? So that's one of the reasons we're using a kind of a regression technique to do the VIF, all right? And so R by itself will tell us the multiple correlation. And R squared, when we square the R of that regression of the independent variable, let's say cylinders over all the other independent variables, then we're going to get R squared, which tells us what is the amount of that independent variable's um, variance is explained by the other independent variables. All right. So, for example, if we took displacement, then the R squared would tell us how much of displacement is explained by the other independent variables, all right? So this is why we used R squared in this case, all right? So, and a question that came in class last week was, if R squared already tells us the amount of variance that an independent variable is explained by the other independent variables, why bother taking the VIF? Like, why do we have to take 1 over 1 minus R squared? The R squared was already a good enough explanation, right? And my answer, and I don't know if I phrased it properly last time, so let me try it again, which is, once we do take the VIF itself has a special meaning that R squared by itself does not give us. And that VIF, and we see these values here, it tells us how much is this standard error inflated by. So one of the things we talked about, we discussed last time, is that these standard errors for these estimates are all going to be inflated. They're going to get bigger if there's multicollinearity present. And the VIF tells us how much bigger it's going to be. And actually, it's not telling us exactly how much bigger the standard error is going to be, but rather how much bigger the square, the variance error is going to be. All right. So the VIF, in a sense, tells us how much bigger these the standard error of our estimates is going to be. So that's why we're looking at the VIF. All right. And when you and I suggested this time just use the VIF function that comes from the car package, and um, and you kind of get these results. It'll give you all the VIFs at once, so you don't have to kind of go in and compute each one by hand by yourself. Okay. So these were the VIF values we got, and there was a really good question on the Canvas board about, hey, it doesn't report VIF, it reports something called GVIF. And there's one more thing. There was kind of like a GVIF with a slightly different exponential term there. Okay, and the reason that this VIF function is returning a GVIF and another thing is because we actually have some variables in this set of independent variables which are not simply present as a single coefficient in our model, but rather has two coefficients in our model. All right. And there's an excellent paper out there which explains why in those situations maybe GVIF is a better explanation. However, for all the however, we didn't really have much collinearity problems with origin. We had collinearity problems with these four variables in particular. I think maybe, oh yeah, these four in particular: cylinders, displacement, horsepower, and weight. Okay. So, and one thing I responded on Canvas is by saying, actually, if you just compute the VIF by hand, the way we did in class, you will get exactly these GVIF values for these variables. Okay. It's just that we cannot compute VIF by hand for this variable because it's a binary variable, and when it becomes the dependent variable in our VIF calculation, well, we can't really do it that way. So GVIF is an attempt to estimate it in a slightly different way. All right. Okay. So, but for the most part, the variables that are problematic, that's these four. We can try to see how we could potentially remove one or more by using the stepwise VIF approach that I described in the homework assignments. All right. All right. And what you probably saw is that the first VIF that was problematic was displacement that had like the highest VIF value. So we removed displacement and we run the VIF analysis again. Um, and we remove the next one, we remove the next one. I think maybe I don't remember the order. The order is not as simple as the numbers you're seeing here. It is not remove this, then remove weight, then remove the other. You have to really remove one at a time to see how the story changes when you've removed that one. Okay. And I think what you found is when you will remove them one at a time, the displacement was the first one to go with a high VIF value. And I think I told you the high VIF values of greater than 4 or 5. The second one was horsepower, and the third one was cylinders. Okay, so these three kind of got removed, and you were left with simply. So this was the final regression model I was left with, and I think it's just about the same for you. It was miles per gallon regressed over weight, acceleration, model year, and factor origin. Okay, and if we take a VIF of these final um, set of independent variables, then these are the VIF values we get, and they're all kind of in the acceptable range. Okay. Did anybody get any slightly different answer? No? Okay. Can I just to make sure you're paying attention, can you just raise your hand if you got the same results as this? Click, 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 click. Okay, thank you so much. I see all your hands. So, all right. So you all got just about the same results as this. Thank you so much. Okay. All right. Um, right. Okay. So, all right. Couple more things. One is that you'll notice that we had to essentially there were four variables that were highly correlated with each other: cylinders, displacement, horsepower, and weight. And essentially, we ended up removing from this set of four, we ended up removing three of them except for weight. Oh, boo. Okay, so we lost like three independent variables, and three out of the four that had high collinearity. All right. Um, and yet, and yet, even despite dropping so many independent variables, and we and including, for example, horsepower, which was like really significant and quite large, in fact. In fact, it was, I think, the second largest after weight. All right, it had the second largest estimate. So even after removing all these, our R squared dropped, but not by a whole lot. Okay, how much is this drop? Let's go ask. So, oops, I just want to see like how much R squared did we lose? Our drop in R squared was less than 1%. It was like 0.0063. Less than 1% of our explanation of miles per gallon's MPG's, log MPG's variance, less than 1% of our explanation is really lost. Okay. So that's not really a big loss. That's we can live with that. All right. And we lost that, but we also we almost entirely got rid of multi-collinearity problems. All right. So what is it worth dropping variables to, to kind of get these results? This is a tough question. So first of all, R squared does not drop much, which means our explanation is almost equally good. However, our explanation is also considerably simpler. We, instead of 1, 2, 3, 4, 5, 6, instead of 7 independent variables, we now only have 4 independent variables. So our explanation is a hell of a lot simpler, and we're explaining almost exactly the same amount of the variance of log miles per gallon. Okay. For many scientists, this shows that the second model, the model with the reduced model, or I'm calling it here the refined model, refined meaning I've taken away some things that are not necessary. The refined model is what we call a parsimonious model, and parsimonious means simpler. All right. It means a little bit more than simpler. In modeling, we say a model is parsimonious if it is simpler than another model, but has just about the same explanatory power. In this case, a very, very similar R squared. Okay. So if if we have two explanations and they're both almost equally good, generally in science, we just prefer the simpler explanation. All right. Any thoughts about why? Why do we prefer the simpler explanation? Why don't we prefer, if they're both equally good, why don't we just pick the more complicated explanation? Any thoughts about this? Anybody? Why do we prefer a simpler explanation over a equally good but more complicated explanation? Any thoughts? I want to hear at least one person's feedback on this. Okay, we got a message. Let me take a look. Interpretation. I love these one-word answers. It leaves a lot for me to interpret. Edgar, could I gently ask you to unmute yourself and just tell me a little bit more? Because that is a really intriguing answer. Right. Yes. Okay. Thank you. Thank you. That's actually a really good answer. Sure. One is that it's much easier to explain to other people. And remember, the point of these models oftentimes is explanatory, meaning we have to explain it to somebody else. So if we have two answers and one is just going to be easier to explain, why not pick the easier one? The other person will also probably understand it a lot better than a complicated answer, right? So fantastic. One answer, and I do agree with that, is it's easier to interpret and therefore easier to explain and transfer your learning and your understanding to other people. All right. So that's a really good answer. Any other answers? Oh, there's another thing in the chat. Is it because if it is more complex, it'll be harder to explore more or hard for people to discuss about? Okay, so the second part of this, so there's it's a two-part answer, which is if it's more complex, it'll be harder to explore more. And the second part is it'll be hard to discuss with other people, for people to discuss about the fitting result. I think the second part is like what sounds similar to what Edgar said about it'll be hard to discuss with other people. Okay. However, I'd like the students to, if you could, could I gently ask you to unmute yourself and explain a little bit about the first part of your answer? Because I really like it, but I want to make sure I understand what you're saying. If it's more complex, it'll be harder to explore more. Could that student please unmute yourself and tell us more? Please. Sorry, my mic is not functioning. Okay. All right. No problem. The student cannot do it. All right. Then I'm free to interpret your answer any way I wish. Okay. Um, if 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 we have two explanations and one is actually much more complicated than the other. Okay. In this case, this is a complicated explanation. This is a simple explanation. Um, the student has said it's is harder to explore more, um, and let me give another explanation of why this is an issue. When you have a more complicated answer, essentially there's more moving parts, there's more variables that you are using to explain the same thing, right? And the danger with a complicated answer is that each one of these parts of the explanation could have problems or complexities associated with it. For example, maybe cylinders, yes, maybe it is a good explanation, but only sometimes, right? So the more our explanation here is built of 7 small explanations, whereas here our explanation is built of 4 small explanations. When your explanation has more parts to it, there's more risk of being wrong. There's more things that could go wrong, okay? And when you have an explanation with fewer parts in it, there's fewer things that could go wrong either now or in the future. All right. So one of the reasons we prefer simpler answers is that there's less that we could be wrong about. Whereas if you give an overly complicated answer with a lot of small parts in it, each of those parts has a risk of being wrong to a certain degree. What is the risk of being wrong? To a certain degree, that risk is kind of measured by the standard error, right? So the standard errors also and t-values and p-values all tell us a little bit of the risks associated with this answer. So the more parts we have, these risks kind of add up. All right. So that's one of the reasons we prefer a simpler explanation over a more complicated explanation. It's a little bit like if you were to buy some kind of device, okay? What device? Let's say this device, my mouse. All right. So let's say I was interested in buying a mouse. All right. Um, and And for those of you on YouTube, you can't see what I'm holding up. I apologize. For those of you on Meet, you can. I'm holding up my mouse, okay? And I happen to have an optical mouse. It has like a little laser in there, and it detects whether it's moving around based on the laser, okay? Now, this is not the first mouse I've ever owned. I used to have another mouse a long time ago. Do I still have it hidden in the drawer somewhere? I don't. And that mouse had like a little wheel on it. How many of you ever had a mouse with a wheel in it? A little show of hands, so everyone knows what I can see that you know what I'm talking about. Uh, I hope it's not telling us your age, but but many of you, okay, so all right, so at least half a dozen of you admit that you've had a mouse with a wheel in it before, had a little rolling wheel that rolled. If you had a mouse like that, you'll know that like every few months, like it got stuck with dirt and grime, and like you had to like remove it and clean it, and like it was kind of messy. All right, so this nowadays optical mice have far fewer problems because there's far fewer moving parts in it. The more parts that are moving in it, the more things that could go wrong. More places dirt could get caught and stuck and things like that. So similarly with our explanations, the more moving parts we have, the more risks we have of things being wrong or things going wrong in future. Okay. So again, we just prefer simpler answers as long as the explanation is almost equally good. And in our case, the two explanations are almost equally good. All right. So this is my explanation of why we are using why we would prefer the second model. All right. We had a couple of chat questions that I'd like to try to respond to. Oh yeah, okay. So Yenu, you asked, what does the G in GVIF stand for? It stands for G. I don't know. I've put a little link down here at the bottom of the slide called VIF metrics. Actually, this is the same link that a student in our class posted on our Canvas board. And let me see if I can go and just take a look at this answer. Okay. So this was on Stack Exchange. Remember, we took a look at Stack Exchange earlier in the semester, and it's great. Okay. Um, and there's a question here about, hey, I'm using the the VIF function, the car package. I'm getting something called gVIF and this VIF raised to a certain power type thing. For those of you curious about what gVIF is for, here's one answer. And what I really love about Stack Exchange is the person answering this, John Fox, I take it, is actually one of the people who came up with the concept of gVIF. And they've given a link to their paper, and it's in here. I think it might download, or I don't know where it's going to go. All right. I have no idea where oh, it is right here. Generalized collinearity diagnostics. It's going to be a highly statistical paper, but you might be able to kind of like glimpse through it to see what its key points are. All right. And essentially, they were trying to come up with a technique where you have, for example, in our case, categorical variables which show up in your results in your regression model with more than one coefficient. Like origin has two coefficients. Okay, so for that purpose, they kind of created gVIF. If we did not have, I believe, if we did not have factor origin in our regression model, the VIF function from the car package would not give us gVIF. It would just give us just one answer for all the variables, just a simple VIF. Okay. However, as I mentioned, the gVIF is interpretable as VIF for all the items that have only one coefficient in the results, which is everything except for factor origin. All right. And I think he wrote that somewhere here. In the case of a variable with a single coefficient, this is usually just VIF. And I kind of confirmed that by hand by looking at some of them. All right. Great. All right. So Metab asks, what if we get a huge drop in R squared after removing the variables based on VIF? And I agree with Edgar's answer that we didn't have a big jump, so we don't have to worry. What if we did? Well, Metab, I have a couple of answers for you. If you are generally going through a process in which you are dropping variables and your R squared is falling, then maybe you need to be a little bit worried that you are dropping things with explanatory power, okay? However, one more thing I want to mention, which I really don't focus much on this class, is that when you're comparing models with different number of explanatory variables, so in this case, we have 4 explanatory variables. Here we have 7 explanatory variables. Generally speaking, we often prefer looking at the adjusted R squared. And all the adjusted R squared does is it takes into consideration that how many independent variables you have, okay? And if you have a lot of independent variables, one of the problems with the regression is if you have a lot of independent variables, your R squared is going to be a little bit bigger for absolutely no reason, all right? So the adjusted R squared kind of punishes you a little bit by bringing it down a little bit, okay? So you'll notice here the adjusted R squared for this model is smaller than the multiple R squared. Because it's adjusting it and saying, I'm going to punish you for having so many explanations in your answer. Down here, you'll notice that it's also smaller, but by far less. Here, the difference between my R squared and adjusted R squared is like it's almost 0.001. Here, it's a little bit bigger. It's like, I'm not sure how much. It's maybe 0.002, not a whole lot. So in these two types of small models, the R squared is also quite comparable. The second answer to your question, Metab, is that if you are using something like stepwise VIF, you probably won't see a big drop in R squared. Why? Because what are we dropping? We're dropping explanations that are highly collinear. They overlap with each other and they're almost the same explanation. So as we are removing them with stepwise VIF, we're not really removing unique explanations. We're removing duplicate explanations. All right, so that's essentially what stepwise VIF is ending up doing. So that's why we're not seeing a big drop in R squared, okay? But that's a great question. If you are using a technique where your R squared or your adjusted R squared is dropping quickly, maybe it's cause for concern and you need to take a pause and ask, is this really what I want to be doing, okay? Do note that if you are using a model for predictive purposes, which we're not really covering in this class, not this semester at least, then it's possible that R squared is not the metric you're really interested in. Maybe it's like an out of sample RMSE or something like that that you're interested in. Okay. All right, cool. All right. Any other questions? Oh, yeah. Okay. The last thing I want to mention is I mentioned that, VIF greater than 4 or 5. Sometimes in literature, I see people say VIF greater than 10 is like really bad. The way to think about why these, I hope whenever you come across this kind of rule of thumb in statistics where someone tells you, oh, bigger than this is bad, smaller than this is good, or vice versa, I hope you don't believe them, okay? Because oftentimes the people making these suggestions don't exactly have a great reason for having these suggestions. So it's often better to try to understand the VIF value for what it is rather than having a rule of thumb. In our case, for example, this is telling us that the error variance of this estimate, not the whole model, but this estimate for displacement. So if you took standard error, which is like the standard deviation of this estimate, and you squared it to make it like the variance of this estimate, that variance is inflated by 30 times. All right. So if you're finding some things are not significant and it has a very high standard error, then and the VIF value is big, then that's cause for concern. All right. In this assignment, I kind of gave you a rule of thumb. I think I said bigger than 4 or 5. Is that what I said? I think that's what I said. I don't exactly remember. Okay. I said bigger than 4 or 5. Why bigger than 4 or 5? Well, you can kind of back trace what happens when VIF is 4 or VIF is 5. Let's say VIF is 5 or bigger. You find that to get a VIF value of 5 or bigger, your R squared needs to be about 80% or larger, meaning that you have an independent variable 80% of its variance is in common with other explanatory variables, with other independent variables. And that's a big amount, okay? In literature, sometimes I find people saying, oh, VIF of 10 is really bad. But when I kind of compute it by hand, that corresponds to like an R squared of 90%. That's not a whole lot bigger than 80%. So to me, even these VIF values are somewhat problematic, all right? Maybe a more rigorous VIF value would be to do something like this. It would be to ask how much of a variance of an independent variable is explained by the other independent variables. Let's say it's more than half. Let's say I have an independent variable and more than half of its variance is explained by other independent variables. This could be a reasonable threshold because we can say, well, this variable is half useless or only half useful, okay? And if that's the case, if we had a VIF value of, excuse me, of, if we have an R squared of an independent variable regressed over other independent variables of 0.05, then our VIF is going to be something like this. Is going to be like 2, right? So even at VIF values of 2, you kind of know that you have some variable whose you have some independent variable, half of whose variance is in common with other independent variables. So it's contributing only half, it's only half meaningful. Let's put it like that, okay? So even with some VIF values of like 1.9, we could be slightly concerned, not overly concerned. So don't take rules of thumb. Whenever you read a rule of thumb like greater than 5, greater than 10, don't take it too literally. Try to understand what it really corresponds to and make your own mind up about whether it's big, important, bad, or whatever it is. All right. I'm not a huge fan of very, very strict rules of thumb that don't have a strong explanation of why it is the way it is. All right. All right. Okay. Whew. All right, so that's my explanation of multicollinearity. And I want to do one more thing before we take a little break, okay? I want to have one more little story before we take a break. And to start that story, I have a question for you all. Is it reasonable to drop explanatory variables? Yes, I know we said the R squared isn't falling. So you can say, yes, it's the same amount of explanation. Fine. But still, I've removed 3 variables, and let's pretend for a moment that we had a discussion with some expert on automobiles, right? We had a discussion with some expert on cars, and that expert told us that, yeah, these are the factors that are really that in from their understanding of like, cars and thermodynamics and like combustion engines and the way they work. This is their expert opinion that these are the factors that are going to be the most important, okay? And now we, maybe non-experts, have just dropped 3 of them. Is that reasonable? Or should we be worried that we've made a mistake by dropping them? So let me just take a little vote here. How many of you think it's reasonable, given everything we've seen, the R squared didn't drop much, it's a simpler explanation, all the stuff I told you, you believe your professor and you think this is a reasonable thing to do to drop these explanatory variables, even though some other expert told us these were the important ones. I'll raise my hand as well because people are shy. Okay? All right? Okay, yeah, you don't have to raise your hand and your virtual hand, but no, keep your hand raised. Keep the raise hand button pressed for a moment. I do want to get an accurate sense of how many people. Okay, so half a dozen people, a little bit more. Oh, it's getting more the longer I wait. Excellent. All right. Okay. Let me. I can remove all your. I'm going to lower all your hands. Okay. Okay. Um, No, no, stop raising your hand. Okay, okay, stop raising your hand. So now let me ask the other question. How many of you think that it is not reasonable, that this could be problematic? So feel free to raise your hand if you think this is problematic. All right, a few people think it's problematic to remove things, right, in this way. Great, great. All right. I think we're seeing just about an equal number of hands, maybe a little bit less here, but maybe like 60-70% of you feel it's reasonable, about 30% of you don't feel it's reasonable. Okay, thank you. You can lower your hand. Actually, I can lower your hands for you. Okay, great. All right. So, all right. Do we have a question? We have a hand raised. If you have a question, feel free to unmute yourself and ask. If you have if I see a raised hand, if anybody has a question, feel free to ask. No? Okay. All right. Hands gone. All right. Okay. Is it reasonable to just drop stuff out of a model like this? Like, is this a problem? Let me make sure the chat window that there's nothing. Okay, it's going on. All right. Okay, there's a question about the intercept. Let me not get to the intercept right now. Maybe we'll talk about it some other time. Okay. Let me just continue with the stream of thought, which is that but yeah, okay. So let me go on a little bit. Okay. So we have dropped variables and our model has completely changed. Is this reasonable? Like, what good is a model if I can just kind of remove things whenever I want? What if my expert came back to me and said, hey, what did you do? You just dropped 3. I just told you 7 important things. You dropped 3 of them, right? And you may say, well, this is an equally good explanation because it's a few simple things. Now, the expert may get back to you and say, yeah, but you know what? I'm not happy that you dropped these 3 because you're right that, cylinders, displacement, and horsepower overlaps in meaning with weight, because the more cylinders you have, the heavier engine you have. The bigger displacement, the heavier engine you have. The more horsepower you have, well, to have more horsepower, maybe you need more cylinders and therefore more displacement, more weight. But these are all but you have to understand that the reason that weight increases is because of cylinders and displacement. So maybe an expert will not be happy that we kind of remove things, all right? However, and let me just check here. The real, yeah, okay, great. So Halim, makes the point that the three variables we dropped, these sound like the root cause of miles per gallon. The weight is just a symptom of having more cylinders, more displacement, and a more powerful horsepower engine. All right. But a statistician may say, yeah, but I've captured the R squared, so we're done. All right. So what is a model exactly? Is a model meant to be a really accurate representation of the world, or is it just a good enough explanation of the world? All right. Um, the answer is really it depends how you're going to use this model. So Halim, your concern is totally right. So Halim's concern is that the reason that some cars got heavy is because more cylinders, more displacement, more horsepower. If we remove these three, then we are removing the rail explanations, even though weight happens to be correlated with all of them. Okay, so I sympathize with you. So then the question becomes, what are you using this model for? Because a model can have multiple uses. Okay, let me show this in a simple explanation that I think everyone will appreciate, because I'll show you a model that you've all seen before and you use all the time, especially if you live in Taipei. All right. So let's take a look at this. In this picture, I think you all know what this is. This is a MRT map, but not of Taipei, because Taipei's MRT map is getting more complicated. I picked a much simpler MRT map and an older one too. Maybe this is not accurate anymore. But this is the MRT map for Athens in Greece. Okay, so Athens, Greece, this is their metro map. All right. What do we use this map for? Well, typically we use a map like this to get from one station to another station, and and where these lines cross, we typically have uh, stations that serve two lines. So, for example, if I wanted to get from, oh my God, I'm going to kill the name, Elinico to Kifisia, I would probably, assuming I know how to read the map, I would take the red line and I would get off at this station right here. And then I would get on the green line and then go to Kifisia. Okay, so that's how I would use this map. This map is a model. This is a model. It's an explanation of the world. And in this case, it's an explanation of the world for people trying to use an MRT. All right. However, is this an accurate model of the world? MRT maps are always made to look really nice and simple with like straight lines, nice curves. If you took this map and tried to represent it more faithfully to the actual distances between the stations and the routes, a more accurate representation, like if you actually if you try to draw the MRT map on a rail map of Greece, it would look more like this. Okay, this is the rail map of Greece, of Athens MRT. If you plotted it on a physical map of a map of physical geography. Okay. I've got a cute little link over here, which I think is really fun to take a look at. Um, Let me hit this. And this kind of shows you the transformation from one map to the other, all right? It kind of shows you this is the simplified map, this is the geographic map. Back to the MRT map, back to the geographic map, all right? Um, so which model is correct? Which of these is an accurate representation of the MRT map? Well, it's tempting to say that this is the better explanation of how the MRT map works. Okay, why? Because this is accurate not only telling you which station is where, but also it's accurate in the sense that it is geographically accurate. All right, so you may feel this is the more accurate map. But you could argue this map is good enough for me if I just want to take the MRT. All right. Um, But my question about what are you going to use it for really comes into play here. For example, let's say I was at Anthopoli and I wanted to go to Kifisia, all right? According to this MRT map, I would have to take the red line all the way to this station. And then from this station, I would have to take the green line back up through to Kifisia. Okay. I cannot just hop off the train here and hop onto the train here. All right. But if you look at this map, it kind of looks like I can do it. It kind of looks like this is possible, right? Because it overlaps there. Let's take let's take some more examples here. All right. Which one are we going to do? Let me try to find an interesting example here. I'm trying to see where it might be. Okay, I have a possible one. I'm not sure if it works. Okay, let's say I want to take the blue line, and for whatever reason, imagine there's a station here. I'm sure there's a station here. Okay, and I decide, hey, I'm going to take the blue line to here, and then at this point, I'm going to jump off the blue line, and I'm going to get on a bicycle, like a U-bike, and I'm just going to bike to the airport. Because look, it's so close. It's so close to each other, right? I can just bike this distance. But if you look at the geographic map, I'm not sure exactly where that curve is, to be quite frank. But that curve might be like over here somewhere for all you know. And if you just did what I just suggested, you may jump off here and then end up having to do a really long bike ride to the airport. You'll be like drained by the time you get here. Okay. You may make a really bad decision if you're using this map. So long story short, this map is great if you're trying to use the MRT stations and the MRT. Not so great if you're trying to get off the MRT and make other decisions. This map is maybe not suitable if you're trying to use the MRT because there could be overlaps that could confuse you and that are wrong. There's no station there potentially. On the other hand, it's probably better if you're trying to do stuff off the MRT. All right. So which map is correct? Well, which model is correct? Well, the statistician George Box has a really nice answer. He says they're all wrong in some way. So there's no such thing as a correct model. They're all wrong. It's just that some of them are useful in some situations. All right. So in this respect, we can kind of like go back to this picture here and say, well, which model is correct? Is it correct to drop it? It really depends. If we're just using this to come up with a statistical model that tells us what can we use to explain things or potentially even to predict things, maybe the second model is good enough, right? It's simpler to explain to people. It's simpler to have an understanding. It might be easier to do a prediction with this even. The first one, however, might be correct if you really want to know what are the actual factors that relates to miles per gallon. An expert has given these to us. So this might be more correct if you really want to have, shall we say, a more faithful explanation of how engines work. All right. So this is kind of my story. I see a raised hand. So could you kindly unmute yourself and ask your question? There's a student with a raised hand. Could you kindly, if your hand is raised, can you just check? Okay, you've got a hand raised, but I think this is not a question. All right. Okay, I'm going to lower the hand. Okay. Um, all right. So which model is correct? It really depends what you're doing with it. It's not reasonable to say that this is the correct model and this is the wrong model. That would not be correct to say. They both have good explanations. We prefer the simpler explanation by and large. However, there could be times when the more complicated example is more useful in a particular way. All right. Um, okay. And so which model do you prefer? It really depends on how you want to interpret it and how you want to use it. We generally, in terms of explanatory models, we don't talk about a single metric to say which one is better or more accurate. Okay, unlike for those of you who have taken data mining or other classes, predictive models where you may look at purely some kind of predictive metric outcome. All right, so with explanatory models, there's no such thing as a correct model. It's really which is the more useful model in your case. But you could use the R squared and other things as part of your deliberation, as part of your calculation of what you think is useful and what is not useful. All right, great. All right, we're going to get into some other topics. I want to talk about residuals and other things. But before we do that, why don't we take a little break, okay? It's 10:20 now. I'd like to take a good 10-minute break. So we'll come back at 10:30 and we'll start discussing the next thing. So I'm going to pause the recording and the streaming. Give yourselves a break. Please keep yourself muted. I do suggest that while you're taking the break, turn your camera off so we don't see you walking into the bathroom or something like that, okay? So feel free to turn your camera off, and I will ask you to turn it back on after the break, all right? So let me stop the recording, and then we will come back in 10 minutes. And Halim, I'm also going to stop